So here we have an example of a ball going in a vertical circle. It says right here that a ball whose weight is 2 newtons, so that's the force of gravity, is attached to the end of the cord whose length is 2 meters as shown. The ball is whirled in a vertical circle clockwise, so it's going that direction. The tension in the cord at the top is 7 newtons, and the tension in the bottom is 15 newtons. So I'm going to go ahead and do a quick free body diagram here. The force of gravity is always down, and that's 2 newtons, they tell us, the weight of the ball. And then up at the top, they say that the tension force is 7 newtons. Now, on the other side over here, we still have a force of gravity, and it's still down, and that's equal to 2 newtons. The tension's always along the string, so that's going to be up, and this time they say that the tension is equal to 15 newtons. And I just drew it really long there to indicate that this tension is greater than that tension over there. So the very first thing that they have here is they have some people arguing over this, and they say that Dominique says the net force on the ball at the top position is 7 newtons, since the net force is the same as the tension, and you are supposed to cross out anything that they say that's incorrect. And the thing that she says that's incorrect is that the net force is the same as the tension, because we have another force involved here, and that is the force of gravity. So that's got to be included. Carlos says, no, the net force on the ball includes the centripetal force, tension, and weight. Centripetal force is not actually a force. Don't put it on your free body diagram. There is no centripetal force on here. Centripetal force is the name we give to another force if it caused something to go in a circle. The tension and the weight are acting downward and have to be added. Then you need to figure out the centripetal force, mv squared over r, and include it in the net force. So Carlos is getting at the right idea. You just don't want to include the centripetal force itself. So when you look at this, for example, on here, how would you set this one up? Well, the centripetal force would be everything that points it towards the center. So it would be the force of gravity plus the tension. Then over here on this case, the centripetal force would be the tension, that's pointing towards the center, but gravity is actually pointing it out the other way. They actually give numbers to this, and we can. So we could solve, in this case, the force of gravity is 2 newtons, and the tension up here, they say, is 7 newtons. So we know that overall up here that the centripetal force is 9 newtons there. Over here in this case, we can see that the tension minus the gravity will be the centripetal force. So it'll be 15 newtons up here minus 2 newtons. So in this case here, the centripetal force is 13 newtons. So it must not be going at constant speed in order to get that to happen there. So next picture that they have is this one right here, and I just want to indicate they say that it's going clockwise, remember, so it's spinning this way. So let's draw some velocity vectors. So at z it's going that way, at m the velocity is down, at q the velocity is to the left, and at p the velocity is up. We could draw some acceleration vectors. The acceleration will always point towards the center of the circle, and by the way, so will the force. So the net force, which we can call the net force a centripetal force since it's causing it to go in a circle, will also always point towards the center there. So we can use that actually to do the free body diagrams on this case right here. So we sort of already just did that with these. We've just got to transfer these over to this one. So on Q, which is at the bottom, it says, we'll draw these pictures here. We would have tension up, and we would have the force of gravity down. By the way, the force of gravity down, I'm going to go ahead and add that to all of them, because in every case, the force of gravity should be straight down, and it should be the same length. Now at point P, that's the one on the side here, the force of gravity will be down, and the tension will be towards the center to the right there. Z's up at the top, so force of gravity is down and tension's down as well. And then over here at M, that is on the right side over here, so the tension would be pointing in towards the center. It says derive an expression for the minimum speed the ball can have at point Z, that's the top, without leaving the circular path. So the top one is right here. So let's write that out again. We know that the sum of the forces is the centripetal force. We include everything as positive that points towards the center. So that is both the tension and the gravity there. Right when it gets to the top of the circle there, the tension will start to drop out. It will disappear. So that disappears, and we can say that the force of gravity alone is the centripetal force. Then let's plug in for each. Force of gravity is mass times gravity, and centripetal force is mv squared over r. So masses actually wind up canceling out on each side of the equation. I'll finish it up here. Solve for v, and you get g times r, square root of that. We actually solved this in class that right before we left. So that is the minimum speed. At that point, that's right where tension becomes 0, and it will start to fall out of the circle there. So the last thing they say here, suppose the string breaks at point P, describe the motion of the ball after it breaks, and basically talk about its position, its velocity, and its acceleration. Well, let's look at this. At point P, it's going up. So in terms of position, it's going to go up for a little bit before it slows down, and then it's going to start to move back down like that. The velocity will instantly start to decrease until it gets to 0, and then it will start to increase coming back down that way. And the acceleration is the same the entire time. G, -10, meaning towards the center of the Earth there. It will stay the entire time.